Finally, we're going to be looking at the Anova process, which provides us with a statistical test to determine whether two or more population means are equal to one another. Now, this Anova word comes from analysis of variance. We just take the AN, the O, and the VA to create Anova. But if you hear Anova, just think analysis of variance. What we're trying to do is analyze the variance within and between samples from different populations. So the simplest way to get our arms around Anova is to work through an example. Let's say that we manage all of the customer service call centers for a large company, and we have one customer service center in the Northeast, one in the Northwest, and one in the Southeast. And what we want to know is whether mean call time differs across these three different call centers. Now, the issue here comes back to this idea of variance. Let's just focus in for a second on the call center in the Northeast. We know that if we take samples of calls from that Northeast call center, we're going to get a bunch of different samples, each of which has its own mean and standard deviation, which means there's variance among samples within the Northeast call center. There's also variance within the Northwest call center and variance within the Southeast call center. And then, of course, we could have variance between the different call centers, depending on which sample we pick from each center. So what we're trying to do here is analyze how much of the variance is coming from within the sample that we take from a call center versus between the samples that we take from each call center. Now, the set of hypotheses that we're going to be testing is always here that the null hypothesis is that the three means are equivalent. So the mean from the Northeast call center is equal to the mean from the Northwest call center, which is equal to the mean from the Southeast call center. In other words, mean call time for the entire population of calls coming out of the Northeast call center is equivalent to mean call time for the entire population of calls coming out of the Northwest call center, and those are both equivalent to population mean for the Southeast call center. So by default here, this is our null hypothesis, which means then that our alternative hypothesis, what we're trying to analyze, is whether there's actually any difference in call time across call centers. So if we say in our null hypothesis that call times are all equivalent, our alternative hypothesis is that these call times are not equivalent. What we've done to try to investigate this set of hypotheses is we've taken a sample from each of the call centers of 10 call times each. Let's say that these call times are in minutes. And now we want to use a statistical test to see if the call times are different across call centers. So to use Anova to do this, the first thing that we need to figure out is how many different groups we have and how many different data points we have within each group. So here we have three groups, the Northeast, Northwest, and Southeast. So we'll say that M is equal to 3. We've taken a sample of 10 calls from each call center. So within each group, we have N equal 10. The sample size is N equals 10. So we have M equals 3 groups, each containing N equals 10 data points. Our next step then is to calculate the mean within each group. So for the Northeast group here, we add up these 10 data points and then divide by 10 to find the mean of the Northeast. So we could think about this here as our sample mean. We could call it X bar for the Northeast. We do the same thing for the Northwest, and so we have a sample mean for the Northwest, and we do the same thing for the Southeast, so we have a sample mean for the Southeast. So mean call time in the Northeast is 3 minutes, mean call time in the Northwest is 6 minutes, mean call time in the Southeast is 4 minutes. Now, of course, just like with all of these statistical tests, the fact that the sample means are different doesn't tell us that we can reject the null and lend support to the alternative hypothesis that the population means are different. Just because the sample means are different doesn't automatically mean the populations are different. We need to show with statistical significance that these sample means are different enough such that we can justify making a conclusion that the associated population means are likely to be different as well. Now, once we have the mean within each group, and remember we can use this analysis of variance process on any number of groups as long as we're using 2 or more groups. So this is a one-way ANOVA that we're performing on 3 groups. There are also 2-way ANOVAs and lots of other ANOVA variations, but right now we're just going to focus on one-way ANOVAs. We happen to be using 3 groups here, and we'll look at how to work through an example with this particular kind of test. Now, back to the means that we've calculated. We have the sample mean for each group. The next thing we need to find is this grand mean. And if you remember before, when we talked about combinations of random variables, we said that the mean of the sum was equal to the sum of the means. So to find this grand mean, all we have to do is take the mean of these three sample means. So we can take 3 plus 6 is 9, plus 4 is 13. 13 divided by 3 sample means is 4.33 repeating. So the grand mean is 4.33 or 4 1/3. We could also have found this value by adding up all 30 data points here. 3 groups times 10 data points each is 30 data points. We could have added up all 30 of these individual values and divided by 30, and we would have found this exact same value for the grand mean. So we can find it either of those two ways, but since we have to calculate the mean of each group anyway, it's a little faster to find the means first and then just add these means together, divide by the number of means to get this grand mean. So this is part 1 of our Anova process. We have 3 more parts. First, we're going to find total sum of squares. Then we're going to find what's called sum of squares within, and then sum of squares between. And then we'll talk about how to bring all of those parts together. So looking at total sum of squares here, these are the calculations already done for us in software in a spreadsheet. But the formula that we use to find all of these values is this one here. So we take the sum of each individual data point minus the grand mean. So we'll say sum x sub I data point minus the grand mean, and then we square that quantity, and then we add up all those squared values here. So you can see that we're getting a sum of squares. The fact that we use the grand mean reminds us that we're calculating here total sum of squares. In other words, we take this first value from the northeast here, 2, and we subtract the grand mean. The value we get, we've recorded right here in our table, negative 2.33. If we look at the last value for the northeast, 3, down here, we take 3 minus 4.33, and we get negative 1.33, and we've recorded that here in our table. If we take the first value for southeast, we take 5 minus the grand mean, 4.33, and we get 0.67. And then if we look at the last value for the southeast here, we take 4 minus the grand mean, 4.33, and we get negative 0.33. So this whole left side of the total sum of squares table gets us all of these values right here, just the x sub I minus the grand mean values. The right side of this table is what we get when we square those values. So we're just taking negative 2.33 and squaring it to get this 5.44. Or down in the lower right here, we're taking negative 0.33 and squaring it to get positive 0.11. So we square all of those values. That gives us now this value, each squared value. And then to find the sum, the whole thing here, we add up everything from this right-hand side, all 30 of these squared values, and we get this value right here. 196.667 or 196 2/3. That is our total sum of squares value. And we should know also that the degrees of freedom for total sum of squares is always m times n minus 1, where m in our case is 3, n is equal to 10. So m is the number of groups, n is the sample size. That's our degrees of freedom for total sum of squares. Now we need sum of squares within, and the calculation here is really similar. Here, basically the idea is that we're taking each data point, so we'll call each data point xi, and we subtract from that the mean for its own data set. So we'll just call this the mean x sub I, and once we find each of those differences, we square those values, and then we add them all up. In other words, we take each data point, so looking here at the northeast, we start at the top of that column. So the first data point for the northeast is 2. We subtract from that this data set's own mean. Its mean is 3. The mean for the northeast is 3. So we take 2 minus 3, that's a negative 1. We square that, we get a positive 1. And so you see those two values recorded here, negative 1 for the first value for the northeast, and then the square of it, positive 1 here on the right-hand side. If we take the last value in the southeast sample, so this 4 at the bottom of the southeast column, we take 4, we subtract its own mean. The mean for the southeast is 4. So we take 4 minus 4, and we get a difference of 0. We square that value, and we still get 0. And we see those two zeros recorded here at the bottom of the southeast column, and then the bottom of this southeast column. These are the differences. These are the squared values. So to get this whole left-hand side of this sum of squares within chart, we find these differences. To get this whole right-hand side, we square those differences and we record those values here on the right-hand side. Then we add up all 30 of these squared values. We take the sum of those squares, and the sum of squares is therefore this entire value here, or in this specific example, 150. The degrees of freedom for sum of squares within is m times quantity n minus 1. And then the last thing we have to do is calculate sum of squares between. So for sum of squares between, for every single data point, we take the mean for the set and we subtract the grand mean. And then we square those values and then we take the full sum. In other words, for the first data point here for the Northeast, the 2 at the top of the Northeast column, we don't actually use this 2 at all. But since we're looking at a data point for the Northeast, we need to use the mean for the Northeast. So the mean is 3. So for this data point right here, we take the mean associated with that group, the mean is 3. We subtract the grand mean of 4.33. So 3 minus 4.33 is negative 1.33. And we see that value right here recorded in the left-hand side of the sum of squares between table. And then we square that negative 1.33 and we get a positive 1.77. And we see that positive squared value here. Now realize that we're always going to get the same value for every data point in the Northeast group because we're always using the same mean for the Northeast and the same grand mean. We're just making this calculation 10 times for all of the 10 data points in the Northeast sample. So this Northeast column over here, where we find this difference right here, we see that same value in the entire Northeast column, that negative 1.33. The same is true for the entire Northwest column. So even though we have these 10 data points here, we're always just using the mean for the Northwest, which is 6. We take 6 minus the grand mean of 4.33, and we get 1.67, and we see that value being recorded for every data point in the sample for the Northwest. So we see the same value repeated 10 times for Northeast, the same value repeated 10 times for the Northwest, and the same value repeated 10 times for the Southeast. And then we square all those values to get the right-hand side of this table, to get this part of our calculation. And so, of course, we see identical values throughout the entire Northeast column, through the entire Northwest column, and through the entire Southeast column. And then we sum up all 30 of these values on the right-hand side of the sum of squares between table to get this entire value here, or in our specific case, the sum there is 46.67. And the degrees of freedom for sum of squares between is m minus 1. Now, that was a lot of numbers that we just threw out, but really the concept that's being conveyed here is actually pretty simple. If we just go back for a second to this sum of squares within chart, basically this whole middle area in red here, all we're trying to look at is the amount of variance within each of these individual groups. If we focus in here on just the Northeast, we know the mean of the Northeast is 3, and then we have 10 data points for the Northeast. So if we want to think about finding the total variance in this Northeast sample, we would just take each of the data points for Northeast, we would subtract the mean for the Northeast, we square that value, and we essentially have a square error. We have a certain amount of variance for each of these data points when we do that same thing. So we can think about the sum of everything in this column right here as all of the variance within the Northeast group. Everything in this column is all of the variance within the Northwest group, and everything in this column is all of the variance within the Southeast group. So if we then add up all three of those together, we're sort of getting a figure or an idea of the total variance that we see inside of each of these individual groups. So the point then is that this calculation is giving us a picture into the variance inside of each group. This calculation is giving us a picture into the variance in between these three groups. And then this is total variance. And what we notice is that, in fact, the sum of squares within and sum of squares between is equivalent to total sum of squares. When we add 150 to 46 2/3, we get 196 2/3. So these two variances add up to total variance. Furthermore, the degrees of freedom will add up the same way. So if we add up the degrees of freedom for sum of squares within and sum of squares between, we will get the degrees of freedom for total sum of squares. We'll see that here if we take m times n minus 1 plus degrees of freedom for sum of squares between m minus 1. If we then expand this, we get mn minus m plus m minus 1. We get these two values to cancel, minus m and plus m, and we get mn minus 1, or the degrees of freedom for total sum of squares. Now, once we have these three values for total sum of squares within, and sum of squares between, we can calculate our test statistic value. And when we use this process of Anova on a one-way analysis of variance, we will use an F statistic, which we calculate this way, where we take sum of squares between divided by its own degrees of freedom, and then we look at the ratio between that and sum of squares within divided by its own degrees of freedom. So in our case, if we plug in what we already know here, we said that sum of squares between was 46 and 2/3, so 46.667 approximately. Remember, in our case, we have three groups, so m is equal to 3, m minus 1 is 2. That's our degrees of freedom for sum of squares between. And then sum of squares within, we have as 150. And then we divide that by its own degrees of freedom, m times n minus 1. Well, m is 3, n is 10. So here we get 10 minus 1, or 9. 9 minus 3 is 27. And when we use a calculator to find this value, we get approximately 4.200. So what we have here with this F statistic is actually a ratio of chi-squared distributions. We talked about chi-squared tests before. The numerator of our F statistic formula here is actually a chi-squared distribution with m minus 1 degrees of freedom, and the denominator of our F statistic is actually a chi-squared distribution with m times n minus 1 degrees of freedom, which means that the F distribution is just a ratio of two chi-squared distributions. Now, when it comes to calculating this F statistic, what we can say is that if the numerator is significantly larger than the denominator, so in our case, our numerator is approximately 23, our denominator is approximately 5, if we're just doing rough math here. If the numerator is significantly larger, what that means is that more variation is explained by the variation between groups than by the variation within groups. Here we're dividing essentially this idea of the variation between groups by essentially this idea of the variation within groups. So we can see, because 23 is significantly larger than 5, that maybe what this F statistic is telling us is that we can explain more of the variation as a difference between groups than within the groups themselves, or just noise in the data. Whereas if we have the opposite scenario, if the denominator here is significantly larger than the numerator, then that means that we find more variation within the groups themselves as opposed to between the groups, which might mean that there isn't necessarily a huge difference between the groups, and therefore that we might have trouble rejecting the null hypothesis. It'll be easier for us to reject the null hypothesis when the numerator here is larger than the denominator, because when the numerator is larger than the denominator, we're going to have a larger F statistic, and the larger the F statistic, the more likely it is that we can reject the null and therefore lend support to our alternative hypothesis. But no matter what we have in the numerator and denominator of our F statistic, what it really comes down to is the actual F statistic that we calculated, in this case about 4.2. Our next step is to look up the critical value in our F table. Let's assume here that at the beginning, when we set up our hypothesis statements, that we chose a significance level, an alpha value of 5%. So alpha is 0.05. There's a different F table for every level of significance alpha. So if we choose alpha equal to 0.05, then we need to go find an F table for alpha equals 0.05. These are very easy to find online. You can quickly find one for alpha equals 0.05 or alpha equals 0.1, all of the common alpha values. So this table here is an F table for this alpha value here. Alpha is 0.05. And what we have to do then is cross-reference the degrees of freedom in our numerator with the degrees of freedom in our denominator. In other words, we're looking at two compared to 27. Now, I've modified this table so that you can see the beginning of it, the top of it, where both the degrees of freedom are equal to 1. So this is always the top left-hand corner of the table. And then I've skipped a bunch of rows to jump down to the rows where we can see that the denominator degree of freedom is 27. So in our case, denominator degrees of freedom is 27. We see that here. And numerator degrees of freedom is 2. So we find that here. And we just find their intersection in our F table for this particular alpha level. And we see that we get a critical value of 3.354. All we have to do now is compare our F statistic to the critical value. In our case, 4.2 is greater than the critical value of 3.354. And whenever the F statistic that we calculate is greater than the critical value, as always, that means that we can reject the null hypothesis, which means that we do, in fact, lend support to the alternative hypothesis that there is actually a statistically significant difference between these three groups, and that the differences that we're seeing is not just caused by variation within the groups or noise within the data. If we get to this point and we realize that we don't have a statistically significant F statistic, we can try to increase the value of the F statistic. We can try to do that either by increasing sample size, or we can try to do that by reducing the variation within each of these groups. Oftentimes that can mean breaking groups down into more homogeneous categories. Maybe, for instance, in our Northeast office, there are two divisions, one division that handles only English-speaking calls and another division that handles calls from international language speakers. We could hypothesize maybe that the international calls take longer because they have to be routed to the appropriate call center representative who can speak that language. So maybe the fact that there's those two departments within this Northeast office is causing more variation in this Northeast data, and we can reduce some of that variation if we segment those two divisions into separate groups, something like that. So those are a couple of things we can look at if we don't find significance when we calculate this F statistic and we want to try running the whole test again. Keep in mind, of course, that we walked through this whole process by hand. We used a spreadsheet to calculate these numbers, but ultimately what it came down to was calculating this F statistic by hand and then looking up our F statistic in comparison to a critical value that we found in a table. Typically, though, that's not the way that we run this Anova process. Of course, typically these days, we're going to do this whole thing with software, which means we'll be able to feed in just our raw data, and the software will immediately be able to give us all of this information we spent time calculating. We'll be able to get the mean for each group, the grand mean, and instantly see total sum of squares within, and sum of squares between. We'll know immediately the value of our F statistic, and the software, instead of looking this statistic up in an F table, it'll calculate automatically the probability, the p-value, of finding an F value that's greater than or equal to the F statistic that we found. If that probability is less than or equal to the alpha value that we set, then the conclusion will be that we can reject the null. But even if we're using software, this is what's actually going on behind the scenes. So this Anova process is extremely powerful. There are many different ways that we can use it. This is just one example of a one-way Anova with 3 groups. But while it is extremely powerful, it does, of course, also have its own limitations. For example, this F test that we ran told us that we could reject this null hypothesis, which means that we can lend support to the idea that the population means are in fact different, that mean call time is different across these 3 call centers. But notice that what it didn't tell us is which means were different. So we don't know if we should conclude that mean call time is different for each of these call centers, or maybe just that, for example, the Northeast and the Southeast have similar mean call times, and maybe the Northwest is the only call center that happens to be an outlier. Maybe that's the only call center that's causing us to make this conclusion that the population means are different, that they're not the same. So to actually figure out which of these call centers is causing the difference, we might need to run another set of tests. But at the very least, this analysis of variance process and understanding of this process gives us a great place to start.